Welcome to today's lecture. So, as we said in the last class, we actually did that how a droplet actually combusts, and we showed that the d square law is still valid. If you recall, this was the equation that we wrote. Where Kc is basically the burning rate. Which is constant in the current case. Okay. Now, remember in previous d square law derivations, we always said that the gas phase is always considered quasi steady, right. So, here also if you take just the ratio of Kc divided by the diffusion, okay, you will get it comes out to be rho g by rho L, which is of the order of 10 to the power of minus 3 to 10 to the power of minus 2. So, it essentially implies that the surface regression, which is given by Kc, okay, is slower than gas diffusion, which is given by d. Okay. So, hence gas phase quasi steadiness still holds. Steadiness still holds, and that was the same of what we got in the droplet vaporization case. Okay. And remember also that Tf was the adiabatic flame temperature, this we wrote in the last class also, flame temperature for this stoichiometric flame. Okay. And during this period of droplet combustion, the regression rate, and this you should remember, the regression rate, the reaction standoff distance ratio, ratio is given by Rf by Rs. So, Rf actually decreases, Rs also decreases by the same amount. So, these and the flame temperature, that is Tf, all remains constant. Please do remember that Rf by Rs remains constant, not Rf by itself. Okay. So, as the droplet shrinks, the flame also shrinks, okay, but this relative ratio is kept the same. Okay. So, and Tf is the flame temperature, that also remains the same, the regression rate which is given by Kc also remains the same. So, all these things are the hallmark of this particular analysis, which is basically the d square law, right. Okay. Now, we take a look at single component droplet vaporization. Component droplet vaporization. Okay. Now, it is very similar to the evaporation case. Evaporation. So, here what is given as mv qv ef effective, this is like your L effective in Schiriniano's notation, this is mv into qv plus 4 pi r square lambda L dt by dr at Rs minus, that is because it is in the liquid phase, got it. Okay. So, in this case, if there is no internal, so this is the heat that is transferred to the liquid phase essentially, right. Okay. So, if there is no internal recirculation, okay, the unsteady or the transient heat transfer is Hd, is given as this, we are writing it within the droplet, okay. This is basically nothing but the slowest limit, because why it is the slowest limit, because the heat is transferred by conduction essentially in this particular case, right. and you have the boundary conditions and the initial conditions that t equal to 0 is equal to T naught everywhere, and at the center of the droplet you know that at r equal to 0 this is equal to 0, this is the boundary condition, that is the initial condition. Okay. So, the source of unsteadiness in this particular problem comes from the decreasing value of r, okay, or the Rs rather, and the continuously changing profile of Ts. So, Ts is a function of time, Rs is a function of time, two main sources of unsteadiness, and this has to be the slowest limit. This is because we have taken only the diffusion to be the carrier. So, the droplet surface gets heated, slowly the heat goes to the center of the droplet, and that is how the heat is actually transferred. There is no recirculation, it is only a plain diffusion or a conduction problem over here, right. Okay. Now, we already know from our droplet vaporization counterpart that if droplet temperature is spatially uniform, which is one of the assumption, okay, if it is like that, but temporally varying, this I am just reminding you, right, temporally varying, you have this mv qv effective is equal to mv qv. If you recall your old notes, you will find that this is what we did. This is Rs cube Cpl then rho L into dTs by dt, right. This is frequently used for determining Ts, and this is roughly what we call the infinite conductivity model also, right. That means there is no temperature variation within the droplet. Okay. So, that is the diffusion limit, this is the infinite conductivity counterpart of the same, right. Okay. Now, if you, that is the diffusion limit. So, like vaporization, you have to solve for all these equations. Okay. Now, we can define the gasification Peclet number. You already know the definition of Peclet number. So, this gasification Peclet number is given by the burning rate Kc divided by alpha L, or the liquid thermal diffusivity. Got it. Now, if this Peclet number pH is much less than 1, this implies a very high value of the thermal diffusivity, right. Because if this is much less than 1, that means Kc is much less than alpha L, which implies that the liquid phase thermal diffusivity is very high, right. So, this would normally lead to your uniform temperature, which is basically this case, right. If the Peclet number is much greater than 1, okay, this should lead to a thermal gradient, leads to thermal gradient inside the liquid phase, to thermal gradient inside the liquid phase. Okay. So, in other words, if this is the droplet, okay, the temperature will go like this, right. This is highest at the surface and lowest at the core, got it. Okay. So, this is comes from the Peclet number argument that we have put forward over here. So, infinite conductivity is the fastest, okay, diffusion limit is the slowest, right. So, both depends on what is your gasification Peclet number, which is nothing but the ratio of the burning rate divided by the thermal diffusivity. So, keeping this in mind, okay, let us now move to the presentation mode. So, this is what we did. Once again, this comes from CK Law's material. So, this is we already put forward in writing that this is basically the unsteady, sorry, let us do the. So, this was basically the unsteady diffusion, unsteady conduction term, okay, and this assumes a continuously regressing droplet layer, and this is the corresponding conduction term of the heat that is actually transferred within the droplet core. So, that is what we did in the write up that we just did right now, and this also we did that if the Peclet number is much less than 1, very high liquid phase thermal diffusion or low gasification, this is an infinite conductivity limit. On the other hand, when Peclet number is much greater than 1, this is a diffusion limit. So, both of these two limits actually determines whether we can take the droplet to be in the infinite conductivity or the diffusion. Diffusion is basically like a spherically symmetric droplet evaporation model. Okay. So, diffusion limit therefore always allows heat diffusion and hence represents the slowest possible limit, while this suggests the fastest possible limit, the infinite conductivity. Okay. So, now if we look at the temperature profiles of the droplet, that how the temperature actually evolves with non-dimensional time, you will find that in the case of your diffusion limit, that is the curve, and in the case of your distillation or the infinite conductivity limit, that is the curve, right. So, what you find is that in the diffusion limit, the temperature initially increases very rapidly, okay, and then it starts to slow up. That is because the core of the droplet starts to heat. So, here the surface temperature rises very fast, right. The core is still does not feel the heat. Okay. Slowly as time goes on, the core temperature also starts to rise. That is also shown in this particular curve. This is the center temperature, only valid for the diffusion limit, because in the case of infinite conductivity limit, there is no difference between surface temperature and core temperature, right, because both are the same, it is spatially uniform. So, here you can see that initially the core temperature hardly rises, that is because the diffusion front has to propagate and reach the droplet center, right, as you know that is given by something like alpha L T, right. Okay. So, there is a little bit of a time lag before the core starts to feel the heat essentially. So, as it starts to feel the heat, the surface temperature slowly starts to slow down and the core temperature starts to go up. Okay. Now, in the case of an infinite conductivity limit, as you can see, the increase in the droplet temperature is more like this, right. So, essentially follows, okay, this is initially slower, this is initially a little slower compared to this. If you look at the difference between the two curves, that is because here the entire thermal mass of the droplet is being heated, right. It is not just not the surface. You have to take into account the full mass of the droplet, because everywhere the temperature is the same. It is not like that the center temperature is lower, right. Everywhere the droplet temperature is like a horizontal line, right, and it just goes up with time. So, therefore, naturally there is a difference. This has got more thermal mass, as a result it takes a lot of time for it to go up, whereas this can go up very fast because only the region very close to the surface is actually heated, okay, and the heating front actually reaches the center only after this particular prescribed time. So, there is quite a bit of a time lag between the two. Okay. So, you can clearly see that in the case of a infinite conductivity model, okay, there is an additional, the increase is initially slow because of the additional heat requirement for the core region. Okay. So, that should be taken into consideration in this particular plot. So, this is just to give you an idea that what happens when you have the two limits. Okay. Now, similar things can be one other interesting observations, and the main observation that I want you to take from this particular thing is that the intense droplet heating that we have, and therefore the rapid increase in the gasification rate, right, during that initial part when the droplet surface temperature is actually growing before it actually flattens out, this contributes to less than 10% of the droplet lifetime, right. So, for 10% of the droplet lifetime, okay, 10% of the droplet lifetime, there is an increase in the gasification rate. After that, the gasification rate becomes quite steady. Okay. So, this rapid increase in gasification rate due to intense heating of the droplet lasts only for 10% of the droplet lifetime. After that, the droplet surface temperature kind of flattens out, as you can see over there, right. And this is also seen in the regression, diameter regression plot. You can see that the droplet, actually this is the line, from this point onwards this is a very linear decrease, right, in the droplet diameter. Do you see that? It is a linear decrease in droplet diameter pretty much after about 10% of the droplet lifetime, after that initial intense heating is over, right. So, and therefore, of course, here also you can see that the diffusion limit is the slowest, the distillation limit or the infinite conductivity limit is the kind of the so you can see these two things comes very close to each other. Okay. So, the main concern over here is that during the intense heating period, okay, the radius regresses linearly with time, and this time period is only 10% of the droplet's total lifetime. That is an important observation. Okay. Now, in single component, these observations are now kind of compiled over here, that for active droplet heating, okay, and gasification, okay, occurs sequentially in the initial 5 to 10% of the droplet lifetime, depending on the fuel volatility, of course, and the initial droplet temperature. So, the active droplet heating and gasification occurs during that period. Okay. So, active droplet heating means the sensible enthalpy transferred to the droplet. Now, that takes place when the temperature is low. A low temperature implies low fuel vapor concentration and consequently slower gasification rate, because if you recall, okay, from the Clausius-Clapeyron, okay, the vaporization rate is a function of the PV saturation, right, and that is a function of the surface temperature essentially, right. So, if the surface temperature is low, because the droplet temperature is not initially at the wet bulb limit, when the surface temperature is low, okay, there is a slower gasification rate, because there is a lower fuel concentration at the surface, right. So, as you increase the droplet heating, or as the droplet surface temperature increases, the gasification rate also increases. Okay. So, as the temperature is increased close to the final value, the heating rate must slow down, while the gasification rate increases because of the higher fuel vapor concentration at the droplet surface. Okay. The bulk gas phase, this is also an important statement, the bulk gas phase combustion characteristics are basically insensitive to the detailed heat transfer processes within the droplet. Got it? So, in the case of the bulk combustion characteristics, they are insensitive to all this, whether you are taking infinite conductivity or diffusion limit, etc., these are mostly insensitive, okay, to the entire thing. This is from the droplet perspective. Okay. This is another important slide which actually we want to bring forward one key factor. Remember, we said that mV is equal to mc. We said that whatever is vaporized actually goes towards burning, okay, right. That is what we said when we actually derived the d square law, but in reality that is not the case. There is, if you recall the droplet graph, this is the flame front, right, this is the inner region, correct. So, this fuel whatever vaporizes from here can actually get accumulated in this region, and not all of them are consumed at the flame front. Okay. So, there can be an accumulation. So, as you know that the d square law takes place that there is no accumulation, right. So, if I divide mc by mv, what you will find is that the straight line is basically your d square law, right, at 1, right. But what you see over here is very interesting. Okay. You see over here, let us not look at this part of the plot, the second one, okay. Let us look at this plot only, the left hand side. Okay. So, the gasification rate at the droplet surface is therefore given as a linear sum of the consumption at the flame front, which is basically mc, and the accumulation and depletion rate at the inner region, right. So, if you have to put it in this particular form, it is basically mc plus this particular term, where Rs and Rf designate the droplet surface and the flame standoff distance. Okay. So, it is basically these two, this is the droplet. So, this is your Rs and this is your Rf, right. Okay. So, what you see in this particular plot, that ideally the ratio should be 1, because that is what d square law actually prescribes. But do you see that, for example, in oxygen depleted environment YO infinity, if the flame is burning, these results are for an heptane droplet in a 300 K atmosphere, okay, 300 K room temperature burning. Okay. So, here if it burns in a low oxygen environment, you see that this ratio approaches 1, but for a significant part of the droplet lifetime it is not, right. It is quite low actually. The consumption rate is only a very small fraction. If you look at these horizontal lines, right, they are only a small fraction of the gasification rate. That would imply that there is a lot of fuel which is basically accumulated in that inner region. Got it, right? Okay. However, it does go and reach as you increase the oxygen concentration, right. As you increase the oxygen concentration, and at around 2.84, this basically becomes flat and very close to 1. That implies that you are approaching an behavior in which there is virtually no accumulation as such. Got it? And the flame standoff distance essentially mimics a very similar characteristics. Okay. So, this flame standoff distance has been normalized by Rs. So, if you recall, Rf by Rs is supposed to remain constant, right. So, but that it does remain constant when the oxygen environment is high. Other than that, it actually changes quite dramatically. Okay. So, the fuel accumulation is a real problem, okay, and if you are burning in a low oxygen environment, right, the flame the fuel consumption rate comes down drastically. Got it? Okay. Now, we so far have only taken into account spherically symmetric model, right, spherically symmetric model. Now, if we include the internal recirculation like what we did in the droplet vaporization case, correct. Okay. Now, in this particular case, if there is a flow around the droplet, which is in the normal cases it is, right, what you will find here is that you can find two kind of characteristics. There will be that internal flow that will be created within the droplet, which is once again represented by the Hill spherical vortex, right, okay, and this is the flame front. In addition, you have this egg shaped flame front, right. So, lot of the flame actually burns in the wake of the droplet, okay, and there we get a lot of soot and other kind of features, right. So, this is a very thin flame that actually burns, but the velocity that is created within the droplet is basically given by the Hill spherical vortex. You can have certain cases, this does not take into account separation, there is no separation, there is no fore and aft asymmetry of the droplet, so to say, right. So, there is no asymmetry. Moment there is asymmetry that you create because of the separation, this is a separation, right, this is a separation bubble that you create in the aft of the droplet. The recirculation structure is a little bit more complicated. Now, you get like 4 recirculation pockets, right. Okay, and there is a clear asymmetry between the vertical. Here of course, it is very symmetrical, this is not symmetrical anymore, and you still get a flame which closely moves towards the droplet. Okay, a lot of the flame burns in the wake. So, this droplet has got a more complex recirculation structure, as you can see, which cannot be represented by a Hill spherical vortex anymore. Got it? But we are mostly concerned with this kind of flame for the ease of doing analysis, right. So, how to analyze this? What does the liquid phase transport do? It effectively reduces the dimension of the diffusive heating, right. So, diffusion, what it does is that the surface temperature skyrockets, right, and then this diffusive front takes some time to propagate to the droplet center, right, with and this length scale is basically L or something like that, right. What does this do is the internal recirculation, because of the convection, they reduce this length scale, the effective length scale of diffusion. So, because we already when we considered the Chiriniano's effective conductivity model, we remember we did something like K effective, which was more than some factor chi into K, right. So, it is very similar to that. It essentially means that your diffusivity is enhanced, right, and it can be enhanced by an order of magnitude also, okay, in certain cases. But how do you write the equation for within the full solution for the energy and the species? You have to take into account these two equations. Once again, you have seen these two equations earlier. This is basically the heat transport equation, this is basically the species. If it is a bicomponent droplet, that means a fuel and some other component, you have to write it for that fuel component over here, right, that we did already earlier. So, you can see that this entirely thing, these two are basically the convective derivative, these two are basically the corresponding diffusion terms, right, and this Vr and V theta are given by the Hill spherical vortex, right. Similarly, we can write the species, we get the Lewis number over here, which is alpha by d, okay, and once again these two terms are basically given by the convective derivative, and this is basically the diffusion term. Once again, the regression rate of the droplet has been included in this particular analysis over here, okay, got it. Okay. So, in the case of when you actually have recirculation within the droplet, you just have to follow the exact same methodology as you did for the droplet evaporation, right, and then you have to, the liquid phase analysis roughly remains unaltered, got it. Okay. We will not cover these, okay. This is also an important thing, that when you actually have a single droplet combustion, we have so far considered that the gas phase does not have in the spherically symmetric model, at least we have considered that the gas phase does not have any external influence from external convection, right, when we did the spherically symmetric droplet, right. So, it was burning in an quiescent environment, right. So, only question of gasification was that Stefan's flow, that surface blowing effect that you had due to evaporation, right. But as we can see, like in the case of evaporation, right, as I gave you that example earlier, if you want to say cool a saucer of milk, okay, how do? You blow air over it, right. So, in this particular case, when you actually have a strong convective environment around the droplet, right, it influences the flame, okay, it influences the droplet burning, okay. Now, due to vigorous burning, external convection generally increases the droplet gasification rate, right. So, the gasification rate, because you are removing that boundary layer, right, you are removing that fuel vapor, so that more and more fuel can actually go in. So, what people have done, there are a lot of empirical correlations. See, the actual analysis of this is a very time consuming affair. So, we are just giving you the gist, where here K naught is basically considered to be the gasification rate in the spherically symmetric limit, that means in the limit when it is burning in a quiescent environment, okay, and this is applicable for both droplet burning as well as droplet evaporation. K is the corresponding burning rate or gasification rate or vaporization rate when you actually have a convection present, right. So, this is given by this particular ratio, and this ratio has been plotted over here, okay. So, this ratio has been plotted over here, and and this is of course for normal gravity and microgravity, let us not go into the details of that. So, for forced convection, this was given by Jerry Faith in 1977, which says that what is the ratio of these two. So, one will become, when this factor becomes equal to very small term, then K and K naught will be the same. Other than that, K is always greater than K naught by some extent, right, because this is a non-zero quantity, right, this cannot be negative, right, this is a non-zero quantity, because Reynolds number, Prandtl number cannot be negative, period, right. So, this will be greater than 1 for all practical purposes, right. So, this was given for forced convection. Similarly, for free convection, we already said, or natural convection, we already defined a number called Grashof number, if you recall earlier, and we said Grashof number of the order of 1 to 10 is kind of not, it's almost similar. So, you can say that it's almost natural evaporation may not have much of a say. So, even in that particular case, in these two are the formulation, as you can see clearly, this is a Grashof number of 1/4 function, this is a Grashof number of half function. This once again is an empirical correlation which says that how the burning is augmented when you actually have natural convection, how burning is augmented when you have forced convection, and this is given in terms of Reynolds number, this is given in terms of Grashof number, the normal quantities. However, it should be noted that if you increase the rate of convection over a droplet, right, there is a limit up to which you can increase its gasification rate. Beyond that, what will happen, the flame will actually extinguish, you will have no flame, right. So, it is almost like blowing off your candle, right. You blow it slowly, what happens is that the candle burns, right. But if you blow very hard at the candle, what will happen? The candle flame will extinguish, right. So, you have to keep that limit into consideration, that the flame may actually get extinct if you have too high of a forced convection, got it. Okay. So, that should be taken into account when you actually do this kind of analysis. So, these are two empirical correlations which were given by Law and Williams and Jerry Faith, okay, which actually tells you that how the burning rate is actually augmented from the spherically symmetric limit, okay, when there is a convection quantity present. Okay. So, this will be the last slide of this particular lecture. So, in a practical situations, however, what you have is that not only you have like a single droplet burning, you actually have a cluster of droplets burning, right. That is what is a normal behavior of a spray. If you look at a spray, you will see that there are hundreds and thousands and millions of droplets which are present, right, okay, and they look like this. So, so you are not able to distinguish the flames properly, right. They are all kind of very close together, they burn as an ensemble, right, rather than as individual pieces. Now, obviously this problem is very complicated because it is 3D, the spacing between the droplets actually matters a lot, and the d square law does not hold here because the separation distance between the droplet surfaces increases as the droplet regresses. So, if you have like two droplets sitting here burning very close to each other, so you may have a common flame which enshrouds the two, right, but as time goes on these two droplets become smaller, right, and their separation distance now has increased. So, you get individual flames on the two droplets, that is also possible, right. So, the minimum so there exists a minimum droplet separation distance below which the individual flames will merge. That means, if the droplets are very close to each other, the flames will kind of join. So, you will not be able to distinguish one flame from the another. So, it is like interacting droplet flames, so to say, right. So, in this particular case, if I plot Kc by Kc isolated, Kc means the burning rate of the ensemble, Kc isolated, that if we take that single droplet out of that, what would be the burning rate. So, in that particular case, what you have is that, okay, if you see, look at this particular curve, one is once again when both are the same, right. So, as you increase your L by D, this L by D is basically this, these are two droplets. So, this is your L and this is your D, right. So, as your L by D ratio increases, right, you approach this value of 1, that means the individual droplet burning behavior is re-established, right. But whenever you are away from where the droplets are very close to each other, your burning rate substantially slows down, right, because it reduces the gasification rate because of the competition for oxygen. Both the droplets are competing for the same oxygen source, right. So, naturally the burning rate is very low, okay, when you have this merged flame, but as you go towards you do proceed towards the value of 1 as you increase by the L by D ratio, right. Okay. So, this is the result for undergoing quasi steady burning, there is no buoyancy effect over here. This actually shows that you do approach the limit of 1, okay, when the separation distance is about 5, got it. All the droplets seems to be approaching that same value, right. So, it is highly dependent on L by D, and the gasification rate is actually substantially lower. You can see it is roughly sometimes 30%, sometimes 50%, right. Okay. So, this is important, the d square law does not hold, interaction reduces the gasification rate, and there is a minimum droplet separation distance below which you cannot identify the two flames together. The two flames gradually demerge, okay, as you increase the L by D ratio depending on whatever is the diameter and the separation distance of the two droplets. Okay. So, we will see in the next class what happens for the rest of the droplet scenarios.